Hi everyone. This video is optional, but it will end with a touching ending. All right, let's try graphing the polar curve r equals 1 plus 2 cosine of theta. First off, we may want to graph r versus theta as Cartesian coordinates using the frame method, Picapia, like in chapter 4, perhaps. And remember, when do we get a new phase? When theta changes quadrant, when r changes direction from increasing to decreasing, or vice versa, or when r changes sign. So over here, it turns out that between 0 and 2 pi, there are actually 6 phases. And beneath, I'm putting the key r values underneath the values of theta where we change phases. All right, so in phase 1, that's straightforward. It goes through quadrant 1, and that's just a single phase because r is decreasing throughout quadrant 1, r stays positive, we're in quadrant 1, it's a single phase. But then phase 2 is short because between here and here, r is positive, but then r changes sign. So when r changes sign, we have a new phase. We're in phase 3 now. We're going to want to find out what a is. That's like a theta intercept or a 0 for r. We want to know where r equals 0. So we're going to find out the value for a here later on. That's where we change phases from phase 2 to phase 3. In phase 3, okay, that takes us up to theta equals pi, which is a quadrantal angle. And remember, when we change quadrants, we have a new phase. So we now go to phase 4. Okay, also, r is now going from decreasing, r changes from decreasing to increasing. That's another reason why we have a new phase. And then at this 0, when r equals 0, all right, r is going from negative to positive. We're changing phases from phase 4 to phase 5, right? And then at 3 pi over 2, a quadrantal angle, we're changing quadrants. So then we enter phase 6. Phase 6, like phase 1, is a very nice phase. It covers a single quadrant. R is monotonic. In this case, it's increasing. It doesn't increase and decrease. It's just increasing. And R stays positive. So we have 6 phases here. All right. Now, it turns out that we get what's called a limacon with a loop, although you should put a bunch of arrows here to indicate orientation. Desmos knows what it looks like. But let's try to trace this out. Okay. So here's my handwritten version. A limacon, like a snail, with a loop, an inner loop. Oh, and guess what you do in calculus? In calculus 2, you're going to find areas, like the area inside the outer curve, maybe the area inside the inner curve, and so forth. All right. Maybe the area between the outer curve and the inner loop. All right, anyway. So why does it look like that? All right. So in phase 1, okay, r is positive but decreasing. All right. We start with, okay, when theta is 0, r is 3. So we start off here, 3 units away from the pole. All right. But in phase 1, r is decreasing. We have that arrow there. R is decreasing until we get r equals 1. When theta equals pi over 2, r equals 1. At the quadrantal angle, pi over 2, we get r equals 1. 1 unit north of the pole. And then in phase 2, all right, we're in quadrant 2, r is positive, and we're moving towards the pole. R is decreasing from 1 to 0. We're moving towards the pole. It turns out that a is 2 pi over 3. R equals 0 at 2 pi over 3. I'll explain that in a minute. So then at 2 pi over 3, we're at the pole. In phase 3, we start this inner loop. Remember, put these arrows here. For each phase, put an arrow. Okay, that's why I put 2 arrows on the circles before. But here, we really need arrows for each phase. Phase 3, put an arrow, all right? Phase 3, okay, we think we're in quadrant 2, but we're actually in quadrant 4, all right? Because r is negative, all right? And we're moving away from the pole, okay? Until we're 1 unit, r equals negative 1, 1 unit away from the pole, where we're here. In phase 4, okay, we're moving towards the pole. We think we're in quadrant, we think we're in quadrant 3, but we're really in quadrant 1 because r is negative. We're moving towards the pole. Put the arrow there. B corresponds to 4 pi over 3, as it turns out. B is 4 pi over 3, as it turns out. That's where R is 0. We hit the pole. So phase 4 ends when we hit the pole, when theta is 4 pi over 3. And then in phase 5, okay, from 4 pi over 3 to 3 pi over 2, right? R increases from 0 to 1. We think we're in quadrant 3, where we are in quadrant 3. So we get this piece here with the arrowhead, phase 5. In phase 6, R is positive, increasing from 1 to 3. We think we're in quadrant 4. We are in quadrant 4. Nice big piece of the outer loop here. Put the arrowhead. Wow. And then by the time you get past 2 pi, you're just retracing this thing. 1, 2, 3, 4, 5, 6. I'll do it again. 1, 2, 3, 4, 5, 6. A limousin with a loop. All right, that's not funny. Now, how do we find A and B? Well, R equals 1 plus 2 cosine of theta. Set R equal to 0. Solve for cosine of theta. Cosine of theta equals negative 1/2. You're solving a trig equation for values of theta between 0 and 2 pi. Where is cosine of theta equal to negative 1/2? At 2 pi over 3. Hold on. At 2 pi over 3 and at 4 pi over 3. A is 2 pi over 3, B is 4 pi over 3. A is 2 pi over 3, B is 4 pi over 3. That tells us where the loop, where the limousin of the loop, where the curve hits the pole. At theta equals 2 pi over 3, we hit the pole. At theta equals 4 pi over 3, we hit the pole. Okay, that determines where we start and end the inner loop. All right. Okay, sometimes it helps to draw these extensions for perspective, like when R is negative. All right. Okay. Now, let's put a slider here. Instead of a 2, what if we have 1.5? Okay, smaller loop. What if that's a 1? That's called a cardioid. It's called a cardioid. That's R equals 1 plus cosine of theta, because it looks like a heart, right? It looks like a heart. So it's called a cardioid. What about 0.7? That's called a dimpled limousin. There's no loop. What if we put a 0 here? That's R equals 1, basically. We get a circle. In fact, you can put an A here as like a coefficient for cosine of theta. Add a slider. When A equals 1, we get the cardioid. Looks like a heart, right? If that number in front of cosine of theta grows, we get a limousin with a loop. Again, going backwards, back to the cardioid. And then if A is less than 1, we get these dimpled limousins. And then if A is 0, we get R equals 1. That's a circle. And then if A is negative, okay, we're getting in different quadrants here. So you have animations based on the changing values of A. All right, so once again, limousin with a loop, cardioid, dimpled limousin, circle, and then in the other direction. Now let's look at this guy. R equals 2 sine of 3 theta. Okay, that's where you have the rapid cycling. You have a short period. 2 pi over 3 is the period. It turns out that you get everything between theta equals 0 and theta equals pi. 6 phases. R changes from increasing to decreasing. R changes sign from positive to negative. R changes quadrant. Also, R changes from decreasing to increasing. R changes sign. R changes from increasing to decreasing. All right, then we hit pi. 6 phases. Look at this. It goes phases. 1, put the arrows on the phases. 1, 2, 3. R is negative here, right? 4, 5, 6, and then we retrace. It's a 3-leafed rose. R equals 2 sine of 3 theta. Three-leaf rose. Again, put the arrows. Now, what if we, instead of a 3 theta, what if we have a 4 theta? It's not 4 leaves, it's 8 leaves. 5 theta, back to 5 leaves. 6, you have 12 leaves. So the rule is that if you have r equals a sine or cosine of n theta, let's assume a is non-zero. If n is odd, you have n leaves. If n is even, you have 2n leaves. Okay, or you could think of it this way. In both cases, you have 2n leaves, but in the n odd case, you have n leaves overlapping on top of n leaves. So once again, for something like this, n equals 2, you have 4 leaves. Okay, n equals 1, you have 1 leaf in a way, right? N equals 2, you have 4 leaves. N equals 3, 3 leaves. N equals 4, 8 leaves. N equals 5, odd, 5 leaves. N equals 6, even, 12 leaves. N equals 7, odd, 7 leaves. N equals 8, even, 16 leaves. Let's go back to 3. N equals 3. Guess what you do in calculus? Find the area in one leaf, and then find the area inside the entire rows. So we end with a romance. I leave you with a rose. Congratulations, that's pre-calculus.